In this video, we will learn about the pH scale, how it's defined, and the pHs of common substances. Generally, when we're talking about pH, we're talking about aqueous solutions, solutions where the solvent is water, H2O. Pure water, at 25 degrees Celsius, has a pH of 7. We typically see solutions with pH values between 0 and 14, with pH 7 being in the middle. The pH of water, pH 7, is considered neutral. A solution with a pH greater than 7 is basic, and a solution with a pH less than 7 is acidic. But what exactly does acidity mean? Generally, an acid is a substance that can lose hydrogen ions. Generally, we use water as a reference. This particular type of acid is known as a Bronsted-Lowry acid. Typically, when we add an acid to water, it will dissolve and dissociate, and the hydrogen ion from the acid becomes attached to a water molecule, forming H3O+, otherwise known as the hydronium ion. And we can write the equation like this: HA aqueous plus H2O liquid react to form A- aqueous plus H3O+ aqueous. In this process, the acid is donating a hydrogen ion to a water molecule. The rest of the acid is simply left behind in solution. To keep things simple, we sometimes don't include the water molecule, instead writing the dissociation of the acid as HA aqueous reacts to form A- aqueous plus H+ aqueous. It's the concentration of these hydrogen ions in solution that determines the acidity and the pH. Let's imagine we have some pure water at 25 degrees Celsius. The hydrogen ion concentration is not actually 0, but it is very small, at 0.0000001 molar, or moles per litre. These hydrogen ions arise because of the natural tendency of water molecules to react with one another. Here we can see one water molecule donating a hydrogen ion to another. For convenience, we can leave out one of the water molecules and instead write the dissociation of water into OH- and H+ ions. This is known as the self-ionization or auto-ionization of water. And if we're being precise, we should include reversible reaction arrows, because water molecules react to produce hydroxide and hydronium ions, but hydroxide ions and hydronium ions can recombine to form water molecules. And when these systems reach equilibrium, we're actually left with significantly more water than hydroxide or hydrogen ions. And the difference is quite dramatic. For each hydrogen ion, we expect there to be about 550 million water molecules. If a given solution has a greater proportion than this of hydrogen ions, it's acidic, but if it has less, it's basic. The acidity, or hydrogen ion concentration of common substances, varies over a wide range. A very acidic solution, like 1 molar hydrochloric acid, would have a very high concentration of H+ ions. 1 molar HCl has 10 million times more hydrogen ions per volume than pure water. While a very basic solution, like 1 molar sodium hydroxide, will have a hydrogen ion concentration much smaller. Compared to water, the concentration of hydrogen ions in 1 molar sodium hydroxide is 10 million times smaller. This means between our extreme solutions, we can see a difference in hydrogen ion concentration of 100,000 billion. That's 1 followed by 14 zeros. This means we'll have a massive variety of acidities when dealing with regular solutions. Rather than use hydrogen ion concentration directly, chemists came up with a better system, pH. pH is just a mathematical tool. It's there to simplify the hydrogen ion concentrations we experience day to day. And here's the formula for pH, which uses the molar concentration of hydrogen ions. Log stands for logarithm. Here we assume it's the base 10. This general mathematical tool is what we're going to be using to simplify hydrogen ion concentrations. The large number 1000 is equivalent to 10 times 10 times 10, which is 10 to the power of 3. The log of 1000 is 3. So the logarithm is a neat function that tells us how many times we need to multiply 10 by itself to get a particular number. Applying logarithms makes big and small numbers easier to manage and compare. We've already seen how hydrogen ion concentration can vary across an awkward range. We can simplify to some degree by expressing these values as powers of 10, but that's not quite good enough. If we then take the logarithm, we end up with much more manageable numbers. And lastly, if we change the sign by applying the negative log of the hydrogen ion concentration, we end up with small, manageable numbers between 0 and 14. We have finally arrived at our pH scale. With this, rather than talking about hydrogen ion concentrations, which vary by powers of 10, we can talk about pH, which varies in ones. The actual pH of a substance will vary depending on the temperature and the concentration, but we can place substances on the pH scale with their typical values. As we've already observed, pure water has a pH of about 7. If you're healthy, your blood pH will be slightly more basic, at about 7.4. Seawater has a pH of about 8.1. A concentrated solution of ammonia will have a pH of about 11.6, and a concentrated solution of sodium hydroxide, which you might use to unclog a drain, would have a pH of about 14. Heading in the other direction, we find milk at a pH of 6.6, which is slightly acidic, while a cup of coffee will have a pH of about 4.5. Lemon juice has a pH of about 2.3, and battery acid, which is sulfuric acid, has a pH of about 0. While it's possible to have pH values above 14 or below 0, it's not that common. There is a related scale that you might come across called the pOH scale. pOH is calculated in the same way as pH, but using the concentration of hydroxide ions instead. pH 0 is equivalent to pOH 14, and pH 14 is equivalent to pOH 0. And we can easily fill in the rest of the scale. A solution with a low pH is acidic, and a solution with a low pOH is basic. And we can see across the scale that the sum of pH and pOH is always 14. And this holds for most common circumstances. So you may find this formula useful when converting between pH and pOH. And the last thing we're going to look at is indicators. This class of chemicals is useful because they'll change colour depending on the pH of the surrounding solution. In a way, indicators react with the surrounding solution, but this reaction is reversible, so no permanent damage occurs to the indicator. One of the most common indicators is phenolphthalein. Phenolphthalein, when added to a solution, will tell you if the solution pH is above 8.2 because it will turn pink. While in solutions with pHs below 8.2, phenolphthalein will have no colour at all. Another common indicator is methyl orange, which in solutions with pHs below 3.1 will appear red. And in solutions with pHs above 4.4, it will be yellow. And in solutions with pHs between 3.1 and 4.4, it's a mixture of red and yellow, so it appears orange. So, in a way, these pH indicators do not tell you the exact pH, they just narrow the range a little. Most indicators only tell you if the pH is above or below a particular value. This is why universal indicator was invented. Universal indicator is a cocktail of different indicators whose colours combine to give a rainbow spectrum across the pH scale. Be careful to remember that the colours associated with a solution of a certain pH are usually the colours of universal indicator. Those colours are not necessarily the colours of solutions with those pH values. We can use chemical indicators to monitor the change in pH of a reaction, for instance between an acid and a base. For example, the reaction of 0.1 molar sodium hydroxide and 0.1 molar HCl can be monitored using universal indicator. We can watch the colour change as we add sodium hydroxide and estimate the pH by looking at colours and the differences between colours. This isn't going to be as accurate as using a pH meter, but it's going to be visually much more interesting. With this concentration of hydrochloric acid and universal indicator, our solution would start off looking orange. This is what we'd expect if the pH was 1. The pH only rises slowly, and we've only reached pH 2 by the time we've consumed 80% of the hydrochloric acid. In this period, we would see the solution gradually turning more and more orange-yellow. As we get closer and closer to neutralizing the acid completely, the colour will change from orange to yellow to green and then bright green. When the hydrochloric acid is completely neutralized and no excess of sodium hydroxide has been added, the pH will be 7. If we continue to add sodium hydroxide, our solution will start to turn basic, becoming blue and then purple. But adding significantly more sodium hydroxide solution is not going to drastically change the pH anymore. We're limited by the 0.1 molar concentration of our stock solution. If instead we'd used a pH meter, we'd be able to trace out the pH much more precisely like this, having a smooth curve and an almost vertical portion in the middle. But in this case, the indicator has still been very useful for telling us roughly what the pH of the solution is. And other indicators can be very useful for telling us when we've reached or just passed a neutralization point. But we're not going to look at that. Instead, let's do some practice. Ocean water has a pH of 8. Is it acidic, basic, or neutral? pH is a measure of acidity. Typically, the range of pH values for solutions is 0 to 14. 7 sits in the middle. The pH of water at 25 degrees Celsius, pH 7, is considered neutral. A solution with a pH less than 7 is acidic, and a solution with a pH greater than 7 is basic. The question tells us that the pH of ocean water is 8, which is greater than 7. Therefore, ocean water is basic. In the next question, we're going to look at more pH ranges. In which range of values would the pH of a basic solution be found? pH is a measure of acidity. Typically, solutions have pH values between 0 and 14. The acidity of a solution increases as its pH decreases, and a solution's basicity increases as its pH increases. We describe any solution whose pH is greater than the pH of pure water as a basic solution. Pure water at 25 degrees Celsius has a pH of 7, and we consider this neutral. So any solution with a pH greater than 7 is basic. The question's asking us for a range of values, not a single value, so we're looking for a range that's open between two values or closed in reference to one value. While the pH scale is regularly only displayed up to pH 14, it doesn't actually stop there. So the best we can do is say that the pH of a basic solution is greater than 7. That's two questions that examined the fundamentals. Now let's have a look at a more practically oriented question. Calcium carbonate will produce a fizz of carbon dioxide when added to lemon juice. Based on this observation, what can be said about the pH of lemon juice? Calcium carbonate is an example of a metal carbonate, and the question tells us that mixing calcium carbonate and lemon juice produces carbon dioxide. This might remind you of the classic reaction of a metal carbonate with an acid, which produces a metal salt, carbon dioxide, and water. There are no observations related to the production of the metal salt or the water because they stay in the liquid, but we do see bubbles of carbon dioxide gas. So the question is pointing us towards the conclusion that lemon juice is acidic. pH is the measure of acidity of a solution. Pure water at 25 degrees Celsius has a pH of 7 and is considered neutral. A solution with a pH of 0 is very acidic, and a solution with pH 14 is very basic. In order to react with the carbonate, lemon juice must have a pH less than 7 and therefore be acidic. Therefore, since lemon juice does react with calcium carbonate, as confirmed by the reduction of carbon dioxide, we know that the pH of lemon juice must be less than 7. With only this observation, this is as precise as we can be. In practice, we'd expect the pH of lemon juice to be meaningfully below 7, because producing carbon dioxide at a visible rate will require a relatively high acidity. For now, less than 7 is the best that we can do. Now let's finish up with the key points. pH is a measure of a solution's acidity. The more acidic it is, the lower the pH will be. pH is calculated by taking the negative logarithm to the base 10 of the hydrogen ion concentration in molars, or moles per litre. We generally find pH values between 0 and 14. Alternatively, we can look at basicity and pOH, which uses the concentration of hydroxide ions instead. pH and pOH increase in opposite directions. And for most common circumstances, the sum of pH and pOH for a single solution will always be 14. The pH of pure water at 25 degrees Celsius, pH 7, is neutral. Acidic solutions have pH less than 7, and basic solutions have pHs greater than 7. And finally, chemical indicators, by their colour, indicate the range of possible pH values for a solution.